This lesson is for section 8.2. We're going to be graphing the sine and cosine functions today. That's actually our main objective here, the one that's listed second, because today we're going to be finding out what the general shape of a sine and cosine function is. So we're going to look at a mother function, and then we're going to use transformations in order to graph any transformation of the sine and cosine function. Our first objective that's listed is to determine the amplitude and period of a function, so we'll begin with that one first. So in our previous lesson we talked about a periodic function, and I showed you a graph similar to the graphs that are depicted below here, but where you can clearly see that after a certain interval your values start to repeat themselves. So in this case here, the period here, if I were to try to find where that pattern is then repeated, this represents that interval. I'm going to call that capital P here. And in this case that would be 1, 2, 3, 4 units. So here my period is 4. Now in function notation we actually write it like this. If f of x plus p is equal to f of x, and this is for all x in the domain of f. So for all x in the domain of f, we say that p would be the period. Now p has to be greater than 0, and it also has to be the smallest number, because I could always say, of course, that p is 8, right? If I were to just say that, oh, look at this, it repeats up over here, but you want to find the smallest value of p. So in this case, the period here would be 4, not 8, because I see the repeated value here. In my other graph, if I look for where that graph repeats itself, here the interval, since it goes from -5 to 1, my period here is 6. Okay? So that's a pretty basic concept. Now, our amplitude of this periodic function is also a pretty basic concept, but if it's centered about the horizontal axis like both of these graphs are, then your amplitude is actually the max height that is achieved above your horizontal axis. So here in this case, it's really hard because I didn't actually put in the value here, but let's say that this is at 1.5. Well, your amplitude here is the highest, your maximum value above the horizontal axis, 1.5. And over here I actually don't even have y values, but let's say that that is 3, and this down here is -3. Well, my amplitude here is 3, and like I said, over here my amplitude is 1.5. But if it's not centered around the horizontal axis, then what you're going to want to do is use this little equation here. It's pretty basic. All you do is you take your max value, subtract your minimum value, and divide it by 2. Now this would be the absolute value of this, because this amplitude is always positive. Alright, so it still works in this case here. If this is 1.5 and this is -1.5, if we take 1.5 minus -1.5 and divide that by 2, we end up with positive 3 in the top. So 3 divided by 2 is 1.5. So our amplitude does match here by using this equation, or looking at where it's centered and then taking the max value. So if it's not centered, in other words, if the graph was like this, it's not centered about the x-axis, then you must use this equation. Okay? Okay, so one of the main objectives for today is to make sure that you can graph a basic sine function. So I want to give you a visual representation of what we're actually doing here before we fill out this table. So I'm going to use this online graphing app to actually show you how the sine function is generated. Here you're going to see a unit circle. Okay, I want you to ignore all the stuff on the left and only pay attention really to the graph part here. But you see a unit circle. Now the radius here is 1, so that's why it's a unit circle. You can clearly see it's 1 in the y direction, but it's not as evident in your x values here, because we're using pi over 2, pi. So it looks like it's in radians, but really these are real numbers. Remember, pi is just 3.14. So I'm just adjusting my scale so that I'm using those convenient values, but these are still real numbers. It's not a radian measure, okay? Because our inputs are real numbers in this chapter. Remember, that's how we slightly change the notation, because we're talking about the arc length as opposed to the radian measure now. Okay, so anyhow, as this point here, this green point, travels around the unit circle, you're going to see a blue sine function pop up. So what that sine function is doing, it's literally taking the values for this coordinate, the y values, and mapping those out along this x-axis. Okay, so as I move this slider here, and you're going to see that point growing here, or not growing, but moving along in the circle, you see that the sine value, this is the sine function, the actual blue part here is the sine function, and I guess if I can go a little bit slower and go back to that pi value here. Okay, so here when the unit circle gets, I can't get it right on there, but I'm trying to get it right on pi here. So you can see that it's right past pi here as well. So it's just mapping, and it's showing you this segment here, right, corresponds to the y value to this green point. And that's the same value as the y value here in this sine function here. So this is the blue sine function, okay? So as I keep going here, and as I get to 2 pi, notice that the values repeat again. So here I'm at 2 pi, right? Well, as I keep going around that circle, I'm just ending back up at the exact same coordinates. So if I extend this here, okay, you're going to keep seeing that sine function continue. Can't fit it all in here, but it just keeps going and going and going and going. So interesting. Now let's backtrack here and go all the way back. Whoops, not that far. So again, you're just seeing a sine function is literally a mapping of what happens to that coordinate as you move around that unit circle. Okay, I could just do this for hours here. It'll give you the exact same sine wave though. So you're seeing this general shape. And again, the period here is 2 pi, because this is where those values, after it reaches 2 pi, the values repeat. So there's the period. Now the amplitude of a sine function is 1, because your max height here is 1, your minimum height here is 1. You subtract those and divide by 2, and you get your amplitude of 1. Okay, so you're going to be able to graph a sine function without using a calculator and without using an online graphing app. So lucky for you, you've already done half of the work in Chapter 7. Now all you have to do is put it together into a coordinate plane. So we've already calculated, all of these inputs here when we had a radian measure of pi over 6 or pi over 4 or pi over 3. We've already done that. Now what we're doing here is having these inputs, instead of being radian measures, these are real numbers. And these correspond to the arc length on our unit circle. But that arc length actually corresponds to a radian measure. So I know that it's a subtle and weird difference, but I still want you to stress that these are real numbers, but that you can think of them in terms of a radian measure, okay? So when we look at, let's say, the sine of pi over 6, that's the same thing that you did last chapter. What is the sine of pi over 6? Well, since it's in a pi over 6 family, it is closest to the x-axis, which means the sine value is the smallest, so it's 1/2. Now, for, x is 0, the input here, obviously when you start on the x-axis, your y output, since it's on the x-axis, is 0 also. For pi over 4, this is your pi over 4 family. It's right in the middle, so that's your middle value of root 2 over 2. The pi over 3 family is the highest point, so that means it's got the highest y value of root 3 over 2. So that's what we're doing here to fill out these values. I'd like you to do that quickly, and as quickly as you can at least. I'm hoping it doesn't take you any more than 30 seconds to do. I'm going to pause the video and I'm going to fill them out real quick. Don't cheat, try them on your own. Okay, boom. These values here are now magically appearing. I hope you didn't cheat and you tried them on your own, because it is good practice. But now let's talk about how we would graph this. So your graphs don't have to be nearly as elaborate as what is depicted here in this picture below. But the reason why these hash marks look the way they are is because what I'm looking at here is an x range up to 2 pi. Okay. And if that's 2 pi, then that would make that obviously pi. It's half the distance. And if I take half the distance between pi and 2 pi, I have 3/2 pi. And half the distance between 0 and pi gives me half pi. Okay, so here are those major coordinates, right? So I want to graph those right away. I have 1/2 pi, and that would give me a coordinate 1/2 pi 1. So I should talk about these values on this side here. This is 1, and down here is -1. That would make this point here 1/2, okay? And this -1/2. Now in between, you've got your middle point on your unit circle, which is going to be root 2 over 2, and your high point, root 3 over 2. So down here I have negative root 2 over 2 and root 3 over 2, negative root 3 over 2. So you know, it kind of makes sense because this value here is 0.5. This is approximately 0.71, and this is approximately 0.87. So, you know, kind of cool that it all fits together. Okay, so like I said, I want to graph those coordinates real quick for you. Pi over 2, 1. We have pi, 0. 3/2 pi, -1. And 2 pi, 0. Now, oh, forgot the first coordinate here, 0, 0. Okay, so if I connect these coordinates here, you know, I could connect them like this. But that's actually not what our sine wave looks like. And you saw that already in, you know, on the computer app that I showed you. But the reason why it looks curved like this is because if you fill in your other coordinates, so let's do that real quickly. This value here, that looks to be about half of this half pi over 2. So if I cut half pi over 2, or I mean pi over 2 in half, I end up with pi over 4. So if I have pi over 4, that means I'm right in the middle, which is that root 2 over 2 value, right? Root 2 over 2 value. And you know, I could keep doing that and demonstrate to you guys. So that next one is 3 pi over 4. And in that case, again, I'm right back at the middle value of about 0.71 right there. So you will see that it is a smooth curve, and that's what your sine curve looks like. So when you're graphing your sine curve, your basic sine curve, what you need to know is that obviously there's an interval of 2 pi. You don't really need to extend beyond that, but you need to make sure that your point always starts, the sine of 0 is equal to 0. Okay, so it has to go through the origin. You have a few key points. You have a max value here. So here's my max, and that coordinate is at pi over 2, 1. I have an x-intercept besides the one at 0, 0. I have another x-intercept at pi and a final x-intercept at 2 pi. So these are very important coordinates. So really all I need to see are your max, and then your other min here is down here at 3/2 pi, -1. Okay, so these are the important coordinates that I would want to see, and you just need to show me that smooth curve for the sine function. Okay, finally, let's find the amplitude and period as well as the domain and range here of the function. Now, I know I talked about amplitude when we first saw the graph, but from here even you can see that the amplitude would be 1. Okay, if we take our max value minus our min value and divide that by 2, we would end up with 1 minus -1, right? Our max value here is 1, our minimum value is -1. Cut that in half and you end up with 1. So our amplitude is 1. Our period is 2 pi. So once we get back to 2 pi here, it's going to repeat, and I could continue to graph that function, boom, 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 look like that. The domain here is all reals, so any real number can be plugged in here, but the range is always going to fall between a +1 and -1. So my range here is from -1 to 1. And that concludes the sine function. So let's move on now to the graph of our cosine function. Okay, so this time we're looking at a unit circle, but it's going to map out the cosine function. So as I move this slider here, and you see that point going around the circle, it's actually taking the cosine of that value, so the x value of that point. Okay, so as you see, it looks similar to the sine function. We do see this curve here, and as soon as we get to 2 pi, it repeats itself. So here I'm up at 0, 1. And at 2 pi, I'm up here at 1 again. So you do get that same period of 2 pi, and it continues to repeat itself. If I were to move this over here, it just keeps going and going in that periodic motion. Okay, so the major difference between the cosine and sine function is where it starts. Our sine function, remember, started at 0, 0. Our cosine function, though, begins at 0, 1. And that's not, you know, it shouldn't be a surprise to you because that is the cosine of 0, it's 1. So that's why we're starting way up here. So we're going to see very similar behavior, okay, in terms of its period as well as its amplitude, but the major difference here is that it starts at 0, 1. Okay, so please go through and fill out this table real quick. I'll do a few of them with you. I do want you to get this extra practice, so again, please don't cheat. Here at x equals 0, the output we already talked about would be 1. But at pi over 6, remember that is the shortest distance away in the y value, but in terms of x, it's the longest, right? So again, that pi over 6 is the low point, which means it has the longest x value. So this would be root 3 over 2. Pi over 4 is right smack dab in the middle, so that's just root 2 over 2. But that pi over 3 is the high point, which means it's got the shortest x value here. So that's 1/2. Okay? So please go ahead, fill out the rest of those values real quick. Okay, here's the table all filled out for you. Now, I know you didn't cheat on this because you just can't get enough of trig values. But the reason why we're doing this is just to get extra practice with those trig values. We certainly don't have to graph every single point here on the graph. That would be a little tedious and very unrealistic for doing multiple problems, especially on your homework or an assessment. So here we go. When we graph a general cosine shape, much like the sine function, we're looking for specific things. Now, we saw that our cosine function had a period of 2 pi, so I'm going to make sure I had that 2 pi there. Now there's going to be 4 important points that occur here, and I'm just going to split up that period here into 4 different parts. So let's cut it in half. I know that this coordinate here should be, mark that as pi. And then this is going to be pi over 2, because I split that in half again. And then I'm going to triple that value. That might be a helpful strategy here to get this point over here, is just to triple it, because you know that that's 1/3 of the period over here. So this value is 3/2 pi. Alright, so we're going to start this graph here at 0, 1. That's where my cosine graph starts. Now, the cosine graph, if I wanted to continue to draw in, fill in some of these points, pi over 6, root 3 over 2, and so on, it would look like this. It comes down to pi over 2, 0, so it has that intercept here at pi over 2, 0. And we continue through here till we get to a minimum at pi -1, and we come back up, hit the x-axis once more, so we have another intercept at 3/2 pi, and we finish the cycle here by coming back up to our max height of 1 at 2 pi. So we have 2 pi 1 here, and that was what, 3/2 0, 3/2 pi 0. Okay, so this is the general shape for your cosine graph. So this is, again, the general shape. And this is something, again, that you need to have kind of memorized so that when you begin to do transformations of this cosine graph, it comes quite easily. So this is the general shape we're looking for, as well as the key points here that I wanted to make sure you illustrate. Oh, I forgot 0, 1 back here as well. So let's talk about the amplitude of this graph. Now, the amplitude is 1. Okay, we have a max height of 1, a minimum height of 1. The amplitude here is 1. Our period, full period, is 2 pi. Our domain is all reals, because this is going to continue just to repeat this pattern here. And our range is between -1 and 1. So very similar to our sine graph. Okay, so we're also going to ask you to be able to graph transformations of the sine and cosine graph. Otherwise, this section would be way too easy, and this whole chapter would be way too easy. So I want you to look again at that graphing app real quick so that you guys can understand what's happening with these general transformations. Okay, so here I've got our basic cosine graph here in red, and I'm going to, if you can see on the left-hand side over here, I'm going to graph another line or another function here, y equals negative cosine of x, and I hope that you remember from our first semester studies that this is just going to reflect it over the x-axis. So as you can see here, it's just been reflected, boom, right over the x-axis, so that now I'm at 0, -1 as opposed to 0, 1. So here you can see that graph here. If I plug in a new value, let's say 2, all that does is it stretches those values and makes it have a higher amplitude, right? So the amplitude changes, but basically all those values now have been stretched by a factor of 2. So instead of being at 1, 0 or 0, -1, now we are at 0, -2. Okay, so coming back to our note sheet, when I want to graph y equals -4 times cosine of x, this will flip it over the x-axis, and this will stretch it by a factor of 4. So when I go to graph this, again, I only want values up to 2 pi. So I'm going to take pi or 2 pi, cut in half, so I have pi, and then cut these in half, so I have half pi and 3/2 pi. Okay. I know that the cosine function typically, I'm going to do this in red, and I'm just going to sketch this really quick, but I know that the cosine function typically goes through and looks like this, right? Well, I don't want to use this because now I'm reflecting it, so now it goes like this, okay? But these values here, my max and mins, are really at 4 and -4. Okay, so let me erase here my original. And darken this real quick. So this is the new sketch for y equals -4 times the cosine of x. So it's supposed to be a pretty brief thing for you to do. It's not anything that looks, you know, in terms of all the values here. You don't have to do what we did here. I'm just showing you how that relates to our sketch and why our sketch looks the way it does. But that's basically all we need, okay? So make sure you're showing the x-intercepts and then clearly define, you know, your max and mins. Okay, now in number 2 here, I have a value on the inside here, sine -2x. Now you've got to do two different things here in order to understand how to graph y equals sine of -2x. Okay, so we're going to come back to the graphing app real quick. So to understand what happens when you input something on the inside here, okay, we're going to take a look at both cosine and sine functions. Now we were looking at the sine, I think, of -2x. But first let's look at what happens to cosine of x. So I'm going to graph cosine of x. So you see it here in the green, okay? That's our general function. Now, if I have the cosine of -x, I'm going to highlight this real quick. Notice how, boom, nothing changes. It's just the purple graph right on top of the green one. And that's because this goes back to the opposite angle identities that we talked about in our previous lesson. The cosine of x is equal to the cosine of the opposite of x, so there shouldn't be any change in the way the graph looks, okay? So again, the cosine of x is equal to the cosine of -x. It just goes back to our opposite angle identities. Now, when I graph sine of x, though, so here's my sine function, and I graph the opposite of x, notice that we have a reflection. It does reflect the graph because the sine of x and the sine of the opposite of x are opposites of one another. Okay, so you do see a reflection here. In other words, this coordinate here, pi over 2 comma -1, is pi over 2 positive 1. Okay, on the graph of sine of x, as opposed to sine of -x here in orange. Okay, now I'm going to turn off this orange one real quick, hide that one. So there's our sine of x again in red. Okay, notice that it does repeat at 2 pi here, right? It starts to repeat those values here. Now, if I highlight sine of 2x, so I'm taking out the fact that it's negative, I just want to look at the fact that you've got a value here in front of that x, the amplitude doesn't change. Okay, we already talked about what happens with the amplitude. You know, when there's a value out in front of cosine or sine, the amplitude will change. So if the value is out in front, then that changes the amplitude. But here, that 2 did not change the amplitude. So what's on the inside, it doesn't change it. What happens is it actually compresses it. So look at your new period. Your period here is only pi, as opposed to, in the red function, 2 pi, right? So our period here is only pi. And that's because it's compressed our function. Okay, so in the blue, like I said, the period here, it repeats, it repeats at pi, that value right there, okay? So at pi over 2, we end up having an x-intercept. We have our max value at pi over 4, 1. So if you look at these values here that are highlighted here, you'll notice that if I take pi and I cut it in half, I get pi over 2. And if I cut this interval in half, I end up with 3 pi over 4. If I cut pi over 2 in half, I end up with pi over 4. So you're going to show these specific coordinates, okay, when you're trying to graph a function. But basically, all that has happened is that this actually compressed it because it took the full, so the red, sorry, I know I'm tracing over two different things, but the red graph here has a period of 2 pi, right? Where our blue only has a period of pi. It literally has cut your period in half and made that pi. So this value here cuts it in half. So we're going to do something real quick to show you algebraically how to figure out what your new period would be. Okay, so we begin by noticing that y equals sine of negative 2x is really the same as the opposite of sine of 2x. So we need to make sure that we really understand these opposite angle identities because it is different and it depends on the type of function whether or not you'll have something like this and you'll actually reflect it. Because again, if it was the cosine of negative 2x, this is just cosine of 2x. So you don't reflect or do anything to it. Okay, now, in this case, we know that in a typical sine graph, we have it going through 0, 0. Here's 2 pi. Here's pi. It would look like this. Okay, that's a typical sine graph. Now, in this case, though, I'm reflecting it, so I will use this shape instead. Okay, so I'm going to erase the red. Now, I also know that this 2x compresses this horizontally. In other words, this is no longer 2 pi and pi. In fact, it ends up being pi, like we saw in the computer app. But we have pi here and pi over 2. If I cut that in half here, I would have 3/4 pi. If I cut this in half, I have pi over 4. Okay, so let's talk about why this is happening algebraically. So we know that in our basic sine curve, so y equals sine of x, it begins its pattern when x is 0, right? And it ends its pattern when x is 2 pi. Therefore, when y equals the sine of 2x, it should also begin its pattern when 2x is equal to 0. So that's why you're seeing x is 0 here. It begins there still. But it should end, right? It ends when 2x equals 2 pi. So if I solve for x here and divide the 2, I end up with pi. So that's why you're literally seeing pi here. If that had been, let's say, 3x, so let's substitute in 3x here. It begins its basic pattern when 3x equals 0. So again, x is still 0. And it ends its basic pattern when 3x is 2 pi. So we'll divide out the 3 here, and we end up with 2/3 pi. So this would take, or that would become our new period, okay? But then after that, let's do this real quick. I would take 2/3 pi, and I would cut that in half to figure out where the, function would look like this. And then I would cut those values in half again. So 2/3 pi divided by 2 is the same as multiplying by its reciprocal. So you're really looking at 1/3 pi, right? Obviously that's pretty easy to do. Take half of 2/3. But still, you need to know how to do that in case you're dealing with more difficult fractions. But anyhow, okay. That's the general idea for how you're going to graph a reflection. So think about what it looks like in terms of, its opposite. Is it an opposite angle identity that you need to use there? Is it transformed horizontally by a horizontal compression? Does the period change? Does the amplitude change? All of those things factor into how you're going to graph. And again, it's just a quick sketch. So these would be all I need to see. Oh, sorry. You know what? I didn't put the values here real quick. That's all I need to see in terms of what this graph here looks like. Okay? All right, that's the end of the lesson. Nice job. I'll see you guys in class tomorrow. It can get tough, so make sure you're asking some really good questions on how to graph this stuff. See you tomorrow.